Namaskar. Thank you, Dr. Basak. And good morning, respected principal, vice principal, young budding scientists, and other dignitaries. I am S.K. Mondal. So today, actually, I will be delivering some interesting topic in front of you. Just a minute. It's still right. We know the world is small, but we are going to much smaller region. In fact, one of the smallest regions of this entire universe, that is atom. And today, you people, you young scientists, we will make our nation. We will make. आवाज कहाँ है? We will make our. There is a lack of energy. I admit there is a lack of energy. So we have to think something which can give us energy, isn't it? See, life cannot run with love, emotions, informations, anything in the world, but only one thing, that is energy. It is very hard to believe, but it is the fact. So, okay, let us have some data on where basically are we on today. See, in every developing country, the development of a nation, that is defined by one particular term, that is very important term, that is called per capita consumption of electricity. Because see, we always talk about electricity because that is the practical measure of all energies. So now this per capita electricity consumption, if you see the worldwide average, that is around 3,200 kilowatt hour per year. Whereas, where do we stand? That is only almost one third of that. Can you believe? It is only 1,200 kilowatt hour per year. Whereas in some of the developed countries, including USA, they have crossed already 10,000 kilowatt hour per year. Although India is the third largest producer of electricity with around 400 gigawatt electrical installed capacity. Now, what are those energy sources? We know that maximum energy in India comes from the fossil fuel, and that comprises to around 60% of the total energy. So only 40% energy we basically tap from other sources. One of them is renewable energy sources, which contributes to 38%. And a very sad figure comes on our face, that is, we tap only 2% of nuclear energy, which is the future of our nation. See, these coal reserves, okay, I agree. I admit that there are huge resources. In fact, 300 billion tons is not a matter of joke. But since this is a fossil fuel, so there is no renewal of this energy. So this will go off. This will basically, this will go on in smoke. So it will sink one day or the other. And plus, this fossil fuel, one main problem is that it will create a huge amount of waste that is not good for our health. And oil, natural gas reserves are also limited source because India is nowhere in a position of oil and natural gas reserves. It causes pollution also because it's a fossil fuel. Hydroelectric potential, that is a good option. Yes, I appreciate this hydroelectric power. So if we can tap it, then there is nothing beyond that. But in India, we don't have much resources on this. In fact, solar energy, wind energy and geothermal energy, these are all basically we are talking about. In fact, solar and wind energy, we have already developed much. But there is certain problems on these two energy sources. That is, one is efficiency is less in case of solar energy as well as wind energy. And lot of land requirement, that is, see that if you want to place some solar energy or wind energy, then you have to place the land suitably so that this energy can be tapped. And also skill, that skill is not present at India in that large or vast way. Solid energy, one more problem that is going to come in maybe 10-15 years. That is a huge problem that has been anticipated. That is all that PV panels, that is photovoltaic panels. So these panels will be having a lot of waste products, and where to deposit all those wastes. So that is a question. In fact, already all the other countries are slowly thinking on this matter. And last of all, there is geothermal energy. So geothermal energy, the technology available to us is not of that level. And this energy source is also having some potential hazard, that is H2S generation, that is hydrogen sulfide generation. So then we have to again think of how to get away from this. So last of all, alternative source of energy is required for us to sustain. Now let us have a look on what is the energy density of so many fuels we have talked about so far. First of all is firewood. That is only 16 millijoule per kg, whereas if you say gradually if you go downwards, then you will see that uranium-235, if you go for fission, then it will generate huge energy. In fact, coal, brown coal, black coal, natural gas, crude oil never stands beside this. It is way ahead. And of course, this energy from again this atomic business, that is fusion, so that you will create, don't mention it, just forget it. It is a huge to the power infinity. Okay, let's have a small comparison that will be understandable for us. It is a very practical measures. If we burn, suppose a 100-watt light bulb using 1 kg of different fuels, then what are the combinations? That is, say, if we burn wood, and by burning the wood, if we light one bulb of 100 watt, then how much it can extend? That is up to only 1.2 days. Whereas, if you see that using coal, okay, it is just 3 times more, that is 3.8 days. But if you consider only natural uranium, so that will give you only 180 years. Only. But what we are thinking of, that is beyond that, and that is if you can tap our huge sources of thorium in India, it can go up to 25,300 years. So this is the comparison. Okay, see, I am not canvassing anything, but this is a fact that nuclear energy is environmental friendly, safe and reliable. Fuel requirement is very less. And fuel abundance, okay, that is a problem for us, but in certain cases, if we can tap our vast reserve of thorium, then it will be abundant fuel. And waste generation is minimum. If you can think, see, waste generation will be suppose if we use fully that nuclear energy for throughout a year, and for a family, that nuclear waste will be only this tip you can see, this tip. And if it is made of, say, iron, so that much weight will be the waste. And if we can separate that some active product from that thorium, in fact that is protactinium, if you can subtract this, then this amount will be, madam might be wearing one ring, maybe, or anybody of you will be wearing a ring. So this ring, how much is the volume? So that much will be the waste generation. Now, where from this nuclear energy comes? Nuclei are made of protons and neutrons, that all of you know. But if you add up all these masses of proton and neutron and you compare with the combined mass of protons and neutrons of a nucleus, then you will find there is a difference. There is a difference means if we add up all the masses, then it will be more than the masses combined together. Then where this mass goes? Where is the difference? Why is that difference? So basically that difference, that causes the energy. And we all know that mass and energy are basically transferable. I mean, if we consider in this universe, this total conservation of mass and energy are constant. So, Dr. Einstein has calculated that this mass, difference in mass, then that is called a mass defect. So that comes as a binding energy which binds the proton and neutron together. Why it is required to bind them? See, basically, protons, all are positively charged. So, as per Coulomb's law, these positively charged ions will always rebel. So, some force should be there to bind them together. So, that is their binding energy. And this binding energy comes from the mass defect, and which can be calculated by using this famous formula. It is basically a phenomenal formula, you can say, that is that energy is equal to delta M into C square, where delta M is the mass defect and C is the speed of light. Now how this fission occurs? You see this green dot. So this is basically a neutron. And if this neutron, it bombards with a particular energy to a particular nucleus of, especially for example, say uranium-235, then it will magically split into two, and it will form some two more or less equal nuclei. That is, for example, maybe krypton and barium. There are so many. That products can be daughter products can be formed. But one of the examples is krypton and barium. So, okay, in an elaborate way, I have shown this, that, see, this is one slow neutron. Is there any pointer? Okay. This is the slow neutron. Yeah, it's coming. I'm audible. So this is a slow neutron, you see. So if this slow neutron, it bombards on this uranium-235, then the fission occurs. And after fission, these two products. Hello. Okay, I'll explain from here. that's better. See, so after fission, these daughter products are formed, and that is a magic that 2 to 3 neutrons, 2 to 3 neutrons, to be specific, 2.46 neutrons gets generated through this one fission reaction, and so this will again bombard on the target material of uranium-235, and they will produce 9 neutrons. So like this, it is a chain reaction. So all these neutrons, within a second, you can see it can create a havoc, and that's why nuclear energy is a very, very dangerous phenomenon. That is right. But we human beings can do anything, all impossibles to possible. So we can control all these uncontrolled reactions in a fashion that it will help us. Now this uranium-235, okay, one typical reaction, okay, I have just shown here. You can see this uranium-235 with neutron bombardment, that is creating these this nuclei, and then 2 neutrons, you can say 2 to 3 neutrons, and huge energy is formed. So this 200 MeV neutrons energy that is getting generated, because see, this energy was earlier used to combine all those protons and neutrons, which now this neutron, since it has created the imbalance, so now this got split and this much energy is evolved. So our aim is to get that energy into a usable form. So that is our aim. And you can imagine this one MeV, that is 10⁻⁻13 joule, and that is for only one fission reaction. So if you convert it, see this 1 MeV into 200 into, see if you multiply this Avogadro's number, so this will be huge per mole. Per mole of uranium-235, that energy produced will be huge. That you can't imagine how much it will be. So you can see, for example, that 1 joule of, see that 3.1 into 10⁻10 fissions, so that you can say in 1 mole of one particular uranium-235. So this will produce 1 joule of heat energy, that using 1.08 kg of fission material, and it will produce 1000 megawatt day of heat energy. So 1 kg of fission material will produce 1000 megawatt day of heat energy. So this coal, if we burn it, 1 kg of fission material, if you use this 1 kg of fission material, so this will be equivalent to burning of 2700 tons of coal. So it is almost, you can say, it is 27 lakhs times more. So now our aim is fixed. We have to tap this energy. By how? But how? Not by making bombs. Okay, one important fact, just I should mention right now, that nuclear energy, unfortunately, it was used for the first time in the universe by making a bomb. And the second step was to make nuclear submarines. So that means initially people were thinking that how to destroy the world. But later on, after maybe Second World War, so people started thinking that somehow this enormous energy is to be utilized. So that is a boon for us. That Hiroshima Nagasaki bomb, that is basically an eye-opener. And after that, we started thinking of utilizing this energy. And slowly, now we are in a position to really, we are expert in getting this fission energy, and we are producing so much electricity, and using so many different types of reactors all over the world. And our next target is to to tap another energy that is much more than this energy, that is called fusion. So still that experiments are going on this, and India is also part of that. Now what is there in nuclear reactor? See, this nuclear reactor basically consists of 4 major parts. One is core, which contains the actual fission material. So that is the fuel, you can say. And moderator, which slows the neutrons. Why to slow the neutrons? अरे भाई मुझे तो fast generate करना है मुझे energy. But you have to slow it down, because see, this uranium-235 has got a property that it has got a maximum inclination for this reaction, fission reaction, for thermal neutrons. This is a new term. What is thermal neutrons and what is fast neutrons? See, fast neutrons basically, whenever a fission reaction occurs, so that time the neutron which is getting generated, they wants to move away from the daughter products. That is called fast neutrons. That is, they are having huge energy in the range of more than 1 MeV up to in tens of MeVs. So these neutrons are basically waste. So we should not concentrate on those neutrons. Those neutrons are to be thermalized. I mean, they are to be, the energy has to be down. They are both hyperactive. So we have to bring it down. And for that, one moderation is required. That means, if I want to go straight through this row, then what will happen? I will just get obstructed first with Prabhakar, then afterwards that young scientist, then next. So automatically, I don't know whether I will be reaching to the last row or not. So that is called moderation. So that means one fast neutron, so that will get basically deflected by all some other nuclei, so that their energy is down. একটা ভিড়ের মধ্যে যখন কেউ যেতে চায়, কেউ সুপার ফাস্ট 100 মিটার রেস নিতে করতে পারবে না, কিছুতেই পারবে না, বিকজ তারা আটকে যাবে মাঝে মধ্যে। সেই জন্য আমাদের কিন্তু ওইটাই দরকার, আমাকে এনার্জিটাকে একটু কম করতে হবে। আর সেই এনার্জি কম করার জন্য হেভি নিউক্লিয়াস নিয়ে চলবে না, যেগুলো আমার লাইট নিউক্লিয়াস, লো জেড ম্যাটেরিয়াল, দ্যাট ইজ বেসিক্যালি you can say hydrogen, deuterium, or to some extent see that polythene, like this. So all these, light Z materials, which are having low atomic numbers. And one more component that is called reflector. Okay, this reflector is not at all useful for large reactors. But for small reactors, okay, like Dhruva, which is a research reactor in India, so we require this reflector. Because, see, neutrons have got a tendency, if there is nothing, then it will escape. So, those neutrons are also to be brought together to the team. We have to bring it to this room, because all those scientists are coming now, just see. They are entering the room. So, they are all reflected neutrons. And if they come to this room, then we are more energetic and we will produce more power, because our numbers are more. So we want to increase the number of neutrons. So for this matter, we require a reflector which surrounds the core basically. And coolant. Obviously, coolant is the main thing through which we extract the power. If there is no coolant, then it will be what? Can you please guess? If there is no coolant, then it will be what? Exactly. It will be atomic bomb, and that's what basically Hiroshima and Nagasaki happened. There was no coolant, nothing, just simply it explodes, and without controlled reaction, simply it blows off everything. So that was our main contributors for a nuclear research reactor. Now let us have a Now, how does a nuclear power plant works? I'll stop talking, you just simply listen to this. Volume बढ़ा दीजिए। नहीं, This is the video.
Energy. The only difference is that the heat, which converts water into steam, is produced. A nuclear power plant works to a large extent like a conventional thermal power plant. Water is converted into steam, which drives a turbine connected to a generator. This generator converts the mechanical energy into electrical energy. The only difference is that the heat, which converts water into steam, is produced by nuclear fission and not by burning coal, natural gas, or biomass. Uranium oxide is compressed into fuel pellets and packed into sealed fuel rods. Multiple rods in turn form fuel elements which are immersed in water within a reactor vessel made of 20 centimeter thick steel. The reactor vessel is subsequently hermetically sealed. The fission of the uranium can now begin by bombarding it with neutrons. In each fission, 2 or 3 neutrons are released. They in turn cause new fissions and thus creating a chain reaction. In a nuclear reactor, it's important that this chain reaction is controlled. After each fission, only one released neutron should cause a new fission. Boric acid in the water of the reactor vessel and lowered control rods absorb the oversupply of neutrons. By lowering all the control rods at the same time, the chain reaction is stopped within 1.3 seconds. A nuclear power plant with a pressurized water reactor has 3 completely separated water circuits: a primary circuit, a secondary circuit, a tertiary circuit. In the primary circuit, the heat released during the fission of the uranium nuclei heats up the water in the reactor vessel to the temperature of 320 degrees Celsius. The pressure regulator keeps everything under high pressure so the water does not boil or form steam, hence the name high pressure reactor. The hot water passes via the primary circuit to a heat exchanger or steam generator. This is a cylindrical device with thousands of pipes in reverse U shape. The water runs through these pipes and gives the heat to the water of the secondary circuit, which flows alongside the exterior of the pipes. The water in the secondary circuit heats up and turns into steam. The steam from the steam generators drives 1 or more steam turbines. These turbines consist of a series of blades installed on a shaft. The high pressure of the steam causes the shaft to rotate very fast. This in turn drives a generator, which ultimately produces electricity. Somewhat like a dynamo on a bicycle, transformers increase the voltage of the electricity produced by the generator, allowing transportation of the electricity to the end users with as little loss as possible. To cool down, the steam coming from the turbines passes through a condenser. The cooling water from the tertiary circuit passes through the tubes of the condenser. The steam from the secondary circuit condenses to water and is returned to the steam generator to be heated again to steam. The warmed cooling water is brought to the cooling tower. There, it cools through contact with an ascending airflow, the natural chimney effect, as it were. The majority of this water is collected in a basin at the bottom of the cooling tower and then returned to the condenser. Only a small part leaves the cooling tower as water vapor.
So, this was a basic functioning of nuclear power reactor. So, I would like to mention only 2 or 3 points. So, in the video, somewhere it was told that there was a pressurizer. Why this pressurizer is required? Because we all know that water, that boiling temperature. So, boiling temperature always increases with increased pressure. So, if we increase the pressure, then we can go high. We can achieve high temperature. So that means if it is pressurized, if the water is pressurized, then I can heat up the water up to a very, very high temperature. And that is what needed for increasing the efficiency of any power plant. Because as you know, this highest operating temperature that governs the efficiency of a power plant. So that is why. And second thing, second thing, actually, what was there? I would like to. Anyway, but that was not a major thing. Yeah. That okay. In one point of time, it was mentioned that fission reactions it produces 2 or 3 neutrons, but we require only 1 neutron. Why? Because then only the chain reaction will occur. It is obvious, no? See, chain you cannot put multiple devices on a single chain, because chain is always consisting of one element after another. So that means 3 neutrons are generated, that is alright, but we have to trap all those neutrons in a non-fission way, so that the only left neutron will be used for the next fission. And this will create next fission, next, like this. So now what are the different types of nuclear reactors? So this I'll just touch upon all this, because I cannot go into so much details, because if I go into this, then it will take days and days. So now, this is the boiling, first of all, this boiling water reactor. In fact, in India, that was our first reactor, that is called boiling water reactor, where there is only one coolant and it gets basically heated, and that steam is formed from that, and that steam is used for it runs to the turbine, and from this turbine that power is generated. And later on, we have adopted this pressurized heavy water reactor, because that is basically a special interest for Indian people, because we want to use the vast reserves of thorium, and for thorium utilization, this plays a major role, that is pressurized heavy water reactors. So that's why the PHWR comes, and later on these pressurized water reactors, and then high temperature gas cooled reactors, liquid metal reactors. This is basically for fast reactors. You can say fast breeder reactors, liquid metal reactors, then advanced gas cooled reactors, that is AGCR, and light water graphite moderated reactors. So apart from that, there are several types of reactors, but as of now, okay, let us continue with this. Now, what is Indian nuclear program? India, we don't have a huge source, reserves of natural uranium. Only limited or moderate reserves are there. But it's a good news for us that we have got a vast thorium reserves. In fact, in the world, we are if I'm not wrong, it is the largest or maybe second or third deposits of thorium. So that is why we have adopted one interesting program that is called 3-stage nuclear program, where in the first stage we use the PHWRs, and in second stage, in breeder reactors, we will breed all those thorium into usable form, that is uranium-233. So thorium to uranium-233, that breeding will be taking place in fast breeder reactors. And in the third stage, the thermal breeders, so these thermal breeder reactors, so they will use this uranium-233 and will continue the power generation, and that will be in sustainable form. In fact, thousands and thousands years we can sustain with this energy cycle if you go on. And if we can install only say 500 to 600 gigawatt electrical energy installed in our country, so that will be just enough. We don't have to go further installation of all power plants and all making junk of that. So that is the thing. And the cost will be very, very justified for that. So, okay, what I talked about, this natural uranium fuel PHWR, that is stage 1, then stage 2 is FBR, that is fast breeder reactors, with plutonium-based fuel obtained from stage 1, and thorium blanket. So in this thorium blanket, basically we are breeding this uranium-233. And then breeder reactors using uranium-233 fuel, so that will be our final goal. Now, energy potential of 3-stage program is placed at more than 8 times the energy potential of coal reserves. Now I'll talk about my reactors where I'm working, that is research reactors. So in Trombay, that is BARC Trombay, so far we are having so many research reactors, but I will mainly concentrate on these 4 reactors, which is Apsara. So this was the first Indian research reactors, and this was built I think in 1956. Already it has been decommissioned. It is a pool type reactor, and maximum power was 1 megawatt, and it used to use enriched uranium of more than 90% enrichment, and that fuel was brought from abroad. It was a light water moderated and cooled. Neutron flux was in the range of 10 to 13 neutrons per centimeter square per second. And after that, after 4 years, we have commissioned one more reactor that is called Cyrus. So that is a 40 megawatt research reactor, but that is a tank type. And here basically this was made in collaboration with Canada. And later on actually this Cyrus had to be shut down because of some political and other issues. Political means that everybody know that nuclear agreement and 123 agreement. So for due to that, basically to get a continuous supply for our other power reactors, so to ensure that we had to shut down this reactor because the fuel of this reactor was supplied from different country, and there was some problem with that reprocessing of those fuels. So now later on, we are having these 2 live reactors that is called Dhruva, and recently we have commissioned one more reactor that is Apsara. So in Dhruva basically, I'm working here. This is a 100 megawatt thermal research reactor, and that is one of the largest research reactors in the world, and where we use natural uranium as fuel. Natural uranium means uranium which is available naturally, where uranium-235 portion is only, can you guess how much? Natural uranium, how much is the uranium-235 portion? It is only less than 0.3%. See, just think. So we are living on that only 0.3%. So in the beginning of the lecture, I told you, we will discuss only about the small matters. So this is the matter. Only 0.3% we are basically tapping. And rest of the component, that is uranium-238, and that is basically, you can say, more than 99.7%. So this is called natural uranium. And if we use natural uranium, then obviously for moderation you have to use some material which will absorb less neutrons. Because these moderators are also having certain things that it will absorb the neutrons, and it will not give some neutrons they will not reduce the energies. Simply they will trap in a non-productive way. So we want that absorption, non-fission absorption or capture to be minimum. So that is why you have to use heavy water. What is heavy water? There is basically nothing but the water, but you can't drink it. It is basically consisting of deuterium and oxygen. So deuterium is one of the isotopes of hydrogen. Now this D2O, that is heavy water, that is very, very useful for moderation. One more thing, we can use light water because this will be less costly, but this light water, if you use it, then you have to use something enriched fuel. That is uranium-235% you have to increase. Anyway, that capability we are having, so we are currently producing this enriched uranium, and this enriched uranium we are using in one of these reactors, research reactors, that is Apsara U. U means upgraded Apsara. So in 2018, we have commissioned one more reactor, that is Apsara U, and it is basically, you can say it is a photocopy of this Apsara, because Apsara was nicest of all the reactors. You can never get so much beautiful, that's why its name is Apsara. So that is why we are going back again to Apsara. Sorry, this spelling, this is misspelled. It is APSARA. So this is again a pool type reactor, and it is a 2 megawatt the power, and it is having low enriched uranium. So low enriched uranium means it is that enrichment of uranium is less than 20%. And all these things are almost same, except this Apsara reactor is having neutron flux of more than 6 times of the earlier Apsara reactor. So, and that is why basically we are getting all this for isotope productions as well as some experiments that is on shielding and new fuel material, everything. So it will be a huge potential for us for our 3-stage nuclear program. So at present, Dhruva and Apsara, they are basically getting used. This is a Dhruva reactor. If you look, it feels like congested, but naturally so many research works are going on, so that is why it has to be congested in a very small space. We have to accommodate all these research instruments. So this already I have covered. This here is for controlling this reactor power. See, we are having a neutron absorbing material, but in Dhruva basically we can change the level of moderator. So by changing the level of moderator, we can control the size of the reactor. So in that way, we are controlling the critical mass of the reactor and we are controlling the power of the reactor. So that is the thing, and we are using that other absorbing material that is called cadmium, and this cadmium is having a very, very strong affinity to all the neutrons, especially thermal neutrons. So once these cadmium rods are put down to the reactor, it will absorb all the neutrons in a very, very short period, less than 2 seconds. So that is for shutting down the reactor. Suppose in case any parameter goes off normal and then one trip signal generates, and for whenever this trip signal generates, these cadmium rods, there are 9 set of rods like this, so this will fall automatically. This does not require any power supply. So it is basically fail-safe mechanism. So in Dhruva, there are certain, you can see these are all the experimental positions. So these are all beam holes called. These beam holes, basically we can put samples and irradiate, and also we can take out the beams from these positions, and the instruments which have shown you that surrounded over all the positions. So all those instruments are basically there are different type of instruments for nuclear physics experiments. And also this Dhruva is utilized for radioisotope production. That is the major part. All these hospitals where basically we give that radiation therapy to all these patients, not only radiation therapy, all the other therapeutic use. So on those parts, basically I think Dr. Samantha, he will explain. Anyway, so I'll just touch upon this. So we produce so many radioisotopes in Dhruva, and that are used for industrial, medical, as well as other purposes. And this Dhruva is a key reactor for doing research on some future nuclear fuel materials, fuel and calandria, all materials. So material testing is being done in Dhruva, and also neutron beam research for getting the different properties of neutron. Especially, you can say the spin. Neutron is having a unique property that is called magnetic spin. So magnetic spin and other studies also we are doing using this neutron beam. And then neutron activation analysis also we do. That is for short-term irradiation, and you see what are the prompt gamma rays are coming, and by analyzing those prompt gammas, we can do further research on these properties of this material and in different atmospheres, environments. And also, this training and manpower development, that is also one of the major utilization in Dhruva. So these are the isotopes. You can see these are very small fraction I have just mentioned here. So like this, total, I think we produce around 70 to 80 isotopes so far we have produced. But major isotopes we produce is molybdenum 99, that is once per week, and almost you can say once per week or twice per week also. And then iodine 131, and then polonium 166, then phosphorus 32, and then samarium, iodine 125, that is also very good isotope that is used for this BT and X-ray sources, and RIA, that is for blood cancers, and scandium and bromium 82, that is also for leak detection and this time residential time distribution measurement, and iridium 192, that is for industrial radiography. So all these important isotopes we are using, and at present we are basically concentrating on producing this molybdenum 99. So this is basically we are going as for a fission route. So this is basically irradiation route, and we are going for a more productive way, that is fission route. And at present I am also working on this. So in Dhruva and Apsara, in both the reactors, we will be producing fission moly trade or fission moly very soon, maybe within 6 months or so. Sorry, actually, what happened? This has got some problem. So the rest of the slides I'll go through this, because here just a minute. There was some problem. So that is why I made a PDF. So only few slides are left. So let's So this is the Apsara reactor overview. You can see I could not find an actual photograph. If you see this from the reactor pool top, this Cherenkov radiation, that blue, that radiation, it's visible. So that photograph, I'm sorry that I could not bring it because it is a lack of time. And then, Apsara also we're doing the same things, but here the one more important thing, that is in Apsara we are doing shielding experiments. So this is very unique things, and these were already done in old Apsara, but this experiment cannot be done in Dhruva. So that is why. And also in Apsara we are producing one radioisotope which is very uncommon, that is copper 64, which is otherwise not possible to irradiate in other reactors. And these are all industrial applications. You do not have to bother right now. But so many things we can do using radioisotopes. It's really useful. And medical applications, obviously, this cobalt-60 source, so that is used for radiation therapy of cancers. So cobalt-60 also we produce in our reactors. And agricultural applications, especially as phosphorus 32. Phosphorus 32 is used for for producing improved mutants of several crops. So that is also very useful, and it is widely used. And now at last we come to the reactor safety part. So in nuclear reactor, the public perception says that it is very unsafe. Okay. We know it is unsafe. But we can tap, we can control, we can restrict, we can arrest all those risks by putting some extra efforts. Just extra efforts in the means of defense in depth. Basically, we have got the philosophy, depth में जाओ, और जब कितना depth तुम जा सकते हो, उतना depth तक हम लोग safety ensure करेंगे. So that is why you can say there are certain things that we first do this robust design. The design will be robust. So all the best quality materials, best factor of safety has been implemented, and then quality assurance with codes and standards, all international codes and standards, and then redundancy and diversity has been provided in all the systems for all safety functions, and then reactor protection system is also there. In case of any abnormal operation, there is an independent protection system with multiple functionalities, redundant systems. It will not depend on a particular system. So suppose if we rely on electrical power supply, then the other safety system will be based on pneumatic supply. Other will be based on passive safety system. So these are all safety systems, reactor protection system. And then engineered safety features. Suppose, everything, सब कुछ है मेरा प्लेस में, but still that accident occurs. Then what will happen? Fuel will melt. And that is the biggest disaster. In fact, in Chernobyl, 3 Mile Island, so this was the problem. And in fact, in Fukushima also. So now somehow we have to address these situations. If that, suppose the fuel melting situation occurs, and it can occur if only suppose your coolant goes out. If the coolant system leaks out, then what will happen? Then there is no coolant. Because now fuel safety comes into picture. So that is why we are having engineered safety features, and that we call it Emergency Core Cooling System, ECCS. And that takes care of all these eventualities, that is including LOCA, that is loss of coolant accident. And there are multiple barriers to prevent escape of radioactivity. First of all, this fuel itself is a barrier. See, radioactivity cannot go inside because fuel itself is cladded with another material, and that is housed inside a reactor, one coolant tube. And tube is also a very strong material. And beyond that coolant tube, we are having calandria vessel. And beyond calandria vessel, we are having that concrete boundaries. And then again the containment. So these are all the boundaries. So that activity cannot escape from my reactor. Even if all the protection systems have gone bad. So whenever a nuclear reactor is designed, we have to think like that. So in short, you see the lengthiest procedure, and that is why nuclear power is, as on date, one of the costliest options. Just because we have to provide all these safety aspects. That is, see, okay, I need not have to because the time is very less now. So, but anyway, I can discuss later on also. So now these are the level of safety. First level safety, second level safety, third level, fourth level, and fifth level is offset emergency response. See, even if suppose everything is in place, still that accident happens, then we have got some emergency provisions, emergency preparedness plan, and emergency offsite responses. How to manage the site and offsite also. That means we cannot afford to harm the public. So that is the thing. And you will not believe that in our reactors, basically for public, we keep that radiation dose as 1 millisievert per year. And 1 millisievert is basically only 40% of the total dose received by cosmic rays. Even if you don't have a reactor, if you just roam around your campus and all, Calcutta, Mumbai, everywhere, so that will be basically 40% of that radiation dose we are giving by this reactor in a year. So it is so less because we can't afford more than that. So this was my last slide, and before concluding, I must say that nuclear energy, first it was utilized for making bomb. Second, it was utilized for making nuclear submarines. Later on, we are on a track that is for producing of power and for benefit of the society. Let us be on the track, and we pray to God that nobody will dare to repeat the first step, that is making a bomb. So we pledge to this that we will be using this nuclear energy for safe purpose. Thank you.
Thank you, Samir, for such a nice presentation. I think many of you have benefited, and we have a lot of questions arising in your mind. So Samir is here, so you can ask one by one any doubts, any further clarification on any topic.
See, any doubts at any time. I am not saying that right now you have to ask me some questions because I would also like to hear different questions because that is called brainstorming. Because see, I am also not a master of this. So if you raise some questions, I will try to give the answers. And not only that, just today within 5 minutes you have to raise. Okay, during this day you just think on it and you can ask me anytime during lunch break, during any breaks. And whenever you get time, you just interrupt me. I'll be here for you. But if you have any ready-made questions, then you can ask me.
Or you want a particular slide on which you have
In
a
English,
doubt or Bangla?
in English, Hindi, or Bengali.
Simple question.
Yeah.
Having
A simple question. How many days you require to prepare a single cobalt source, cobalt 60, to supply it to the medical institute?
So that's a very relevant question. Yeah, this cobalt actually what happens is that depends on how much specific activity is needed. So based on that, in fact, our reactor is rated at 100 megawatt. So that depends on that at that particular installation time, how much was my reactor power. And suppose if it gets that power is getting lowered due to some other reasons, due to some operational reasons, so that time that is to be also calculated. So in that way, they normally give us one reactor megawatt day data. That is how much reactor megawatt into number of days. So that will give us, and accordingly we operate the reactor and we irradiate those target samples for this much duration to achieve that. So that depends on your how much specific, curie per gram. So that is important for us. Accordingly, we will select for how many days. So for cobalt, basically, see, we have irradiated cobalt pencils also in cobalt slug rods. So that was irradiated for more than 2 to 3 years to get that particular specific energy target. So, in fact, we are also producing nowadays in one of the positions specially dedicated for making cobalt isotopes, and that is a huge specific activity that is more than 300 curie per gram. So that we are achieving, and already we are just nearing that target. That irradiation. So soon we will deliver these isotopes to BRIT, that is Board of Radiation and Isotope Technology.
So it seems that you understood each and everything. There is no question.
I also don't understood. If you understood, then okay, I will still have some questions.
Yes, sir. Yes, yes.
Hello, sir. I just wanted to ask, you said that some isotopes can only be produced in Apsara U reactor and not in Bhabha. I did not understand because both are coming from the fission of uranium-235.
Yeah, that's right. Okay, but there is certain limitation in our this thing. Okay, as of now, we have tried in Apsara, and that was basically it was very fruitful. See, all these things depends on. See, Dhruva and Apsara, there is a major difference in operational flexibility. So, due to that, Apsara is more useful for producing certain isotopes. So, which we have explored, and we have found that is more effective in Apsara due to operational flexibility. Yeah.
So theoretically you can generate here, but practically there is some difference. The purpose are different. That's why we have.
Future, what are you thinking about the generic medicines?
Generic medicines? No, I didn't get your generic medicines. See, okay, I don't know. Regarding medicines, no, if you want to ask anything, then I think someone.
There is nuclear medicines.
Yeah.
And you are researching, your project is going on some nuclear medicines also. So,
Yes, so that.
actions with generic medicines, definitely.
I have no idea. See, in fact, this part is, yeah, please let us know.
generic medicines in the sense we mention that term for a common name of a particular medicine. See, different companies produces a particular molecules of drugs. So they have a scientific name, and when a company produces that drug, they give a brand name. That brand name is not generic, but the formula of that medicine or drug is generic. So when you specify by that formula, that's called generic medicine. Got my point? So there is nothing called generic medicine which is applicable for any general purpose thing. It's not like that. It's a term generic called by the particular medicine.
See, basically, I am in the engineering sector. So still, I try to explain so many things related to physics, which I basically, yeah. Actually, one more question.
You have said that you didn't identify this very less amount.
Sorry.
Hello?
Yeah.
So you have said that uranium-235 is very less in amount available in nature. So why do we need uranium-235? Why are we concentrating on uranium-235 so much? Uranium-238 is available, so what's the point?
Yeah, that's a very good question. I appreciate. See, basically what happens now, we have to start with the basic. Basic means natural uranium which is available to us. I think in India that reserves is around 78,000 tons only as of now. So now this uranium, natural uranium, so that is readily available from this nature, no? So that we will use it first. And see this, enrichment, that technology is basically it is a challenging technology. So it was not readily available to us, and we developed ourselves to enrich uranium. So uranium enrichment up to today's achievement, so that took a long time. So that is why basically we ourselves could not go initially for Apsara type reactors where we use this enriched uranium. In fact, for your information, nowadays there is no reactor operating in the world which uses so much enrichment, that is more than 90%. See, due to some treaty, international treaty, now this usage of uranium enrichment that has been limited to only 20%. So you cannot go beyond 20% because beyond 20% enrichment means it is a nuclear bomb grade. So that is why to avoid nuclear proliferation, so we don't go beyond 20% enrichment. But at present, we are able to achieve the target. So now Apsara type reactors are very good. And in fact, we are using the PWRs, that is pressurized water reactors, where we use water as a coolant and moderator. So there we can afford, and we are using also.
By enrichment, we can use uranium-238. We can make use of uranium-238.
No. By enrichment, we are using basically uranium-235. Ultimately fission with thermal neutrons, that will be much more with uranium-235 compared to 238. 238 is having some tendency for fast neutrons, but not in a very large scale. 238. But 235, it has got a huge potential for thermal neutrons. So all of a sudden you can see one spike is there for uranium 235. So that is why 235 is used. That is for, as on today, for practical purposes. And one more isotope is there, that is uranium-233. That is also readily, fissionable. See, these materials which are having odd mass numbers. That is 235, 239, then 233. So all these odd numbers, plutonium-239. So all these things are called fissile material. Fissile means they are just ready to fission. But otherwise, all the other materials, that is including uranium-238, first it has to be converted to an odd mass number, that is uranium-239, and then it will go fission. So like this. So uranium-232, which is readily available in India in vast figures. So this 232 you cannot use for power production right now because they are not basically, they cannot go directly into fission because it is an even number 232. So it has to be first, converted to some odd number that is called uranium-233. Then uranium-233 will be used for, and that is a fissile material, uranium-233.